15 pounds per square inch. That is the weight of a large bowling ball sitting on a patch of skin no bigger than a postage stamp. And you have got, roughly 2,700 square inches of skin on your body. So if you multiply that out, you get something close to 40,000 pounds of total force. That is 20 tons. 20 tons of air squeezing you from every direction right now as you sit there doing absolutely nothing about it. So why are you not a pancake? That is the question. And I will tell you something. The answer most people give is wrong. Not completely wrong, partly right, which is almost worse because partly right makes you feel like you understand something when you do not. And that feeling, that comfortable, satisfied feeling of almost understanding, that is the most dangerous place in all of physics. So let me first tell you the wrong answer because it sounds very good. I want you to feel how good it sounds. I want you to nod your head and think, yes, of course, that is obviously right. And then I am going to take it away from you. The wrong answer goes like this. The pressure pushes on you equally from all sides, up and down, left and right, front and back, and because the forces are equal in every direction, they cancel out, so you feel nothing. The net force is zero. Sounds beautiful, does it not? Symmetric, balanced, the kind of thing a physics teacher puts on a chalkboard with a nice little diagram, arrows pointing inward from all directions, same length, and writes net force equals zero at the bottom with a satisfying tap of the chalk. Done. The students write it down, the teacher moves on. Everyone is happy, and nobody has actually learned what is going on. Let me show you why. Take a grape. A single ordinary grape. I want you to imagine putting that grape at the bottom of the ocean, down where the pressure is, say, 500 atmospheres. That is over 7,000 pounds per square inch pressing on that grape from all sides. Equally, symmetric, forces balanced. The grape is fine. It looks exactly the same as it did at the surface. It may be the tiniest bit smaller because water is slightly compressible at very high pressures, but you would barely notice. The grape is not crushed, it is not flattened, it is a grape. Now take a sealed, air-filled glass jar and send it down to the same depth, same pressure, same symmetry, same balance forces on all sides. That jar shatters, explodes inward, destroyed completely. What is the difference? The grape is full of stuff. It is full of water, pulp, sugars, all at whatever pressure surrounds it, because those materials are nearly incompressible and they transmit the pressure instantly throughout their volume. The inside of the grape is at the same pressure as the outside. The jar, on the other hand, has a pocket of air inside at 1 atmosphere, while the outside is at 500 atmospheres. There is an enormous difference between inside and outside, and that difference is what breaks it. Equal pressure from all sides does not protect you. Equal pressure on both sides of every boundary in your body, that is what protects you. The distinction is crucial, and most explanations skip right over it. But I am getting ahead of myself. Let me go back to the very beginning and do this properly, step by step, because the real story is richer than any shortcut. Let us start with what pressure actually is. Forget the formulas for a moment. Just picture what is happening at the level of the atoms. You are surrounded by air. Air is made of molecules, mostly nitrogen and oxygen, zipping around at tremendous speeds. At room temperature, the average air molecule is traveling at something like 1,100 miles per hour, faster than a rifle bullet. In every direction, completely at random, and there are a staggering number of them. In a single cubic centimeter of air, a little cube about the size of a sugar cube, there are roughly 27 billion molecules. 27 followed by 18 zeros. Each one of these molecules is flying around, banging into the walls, into your skin, into the table, into other molecules, bouncing off and flying away, only to come smashing back a fraction of a second later. Each individual collision delivers a minuscule push. Truly tiny. But there are so many of them, trillions upon trillions, every fraction of a second on every square inch of surface, that the combined effect of all those tiny pushes adds up to something enormous. That combined push per unit area is what we call pressure. At sea level, the air molecules are packed tightly enough and moving fast enough that their combined hammering on each square inch of any surface amounts to about 14.7 pounds. That number has a name. We call it 1 atmosphere, and that number is, when you stop to think about it, surprisingly large. Think about the palm of your hand. Your palm is maybe 10 square inches. That means the air is pushing on just the palm of your hand with a force of about 150 pounds. That is like having a grown adult standing on your palm. Your entire body. That is like having a mid-sized automobile balanced on you. And yet here you sit, comfortable, not even slightly inconvenienced. Let me take the standard answer out for a spin, because the arithmetic part is fine. It is the interpretation that goes wrong. The air pushes down on the top of your hand with 150 pounds, but it also pushes up on the bottom of your hand with 150 pounds. So the net force on your hand is zero. Your hand is being squeezed, yes, but not pushed in any particular direction. True, correct, I do not argue with any of that. But now I want you to think about a submarine. A submarine, sitting at the bottom of the ocean, has water pressing on it equally from all sides too. Left, right, top, bottom, front, back. The pressure of the ocean is symmetric around that submarine, just like the air pressure is symmetric around you. And yet, if you go deep enough, the submarine gets crushed. The hull crumples inward, the steel buckles, rivets pop, and everything inside is destroyed. There are photographs of deep-sea submersibles that failed. The wreckage looks like someone stepped on a soda can. Equal pressure from all sides. And it got crushed anyway. So much for the forces cancel out. The forces did cancel in terms of net translational force. The submarine was not pushed sideways or downward by the pressure. It stayed right where it was, but it was compressed, squeezed smaller, crushed. The balance forces did not prevent that. Something is wrong with our reasoning. Or rather, something is missing. And what is missing is, I think, the most interesting part of this whole business. Here is what is actually going on, and it is so simple that it is almost embarrassing once you see it. Your body is already pressurized from the inside. Think about what you are made of. You are not a hollow shell like the submarine. You are not an empty jar like the glass one we sent to the bottom of the ocean. You are mostly water. About 60% of your body weight is water. Water filling your cells, your blood vessels, the spaces between your organs. And water as a liquid is nearly incompressible. If you try to squeeze a bag of water, it pushes back immediately and completely. You cannot significantly change its volume no matter how much external force you apply. A hydraulic brake system in a car uses this exact principle. You press a pedal, the force transmits through fluid to the brake pads instantaneously and without loss, because the fluid does not compress. So your body, filled with water and other incompressible fluids, is at atmospheric pressure on the inside. Every cell, every blood vessel, every drop of fluid inside you is being pushed outward with the same 14.7 pounds per square inch that the air is pushing inward. The inside matches the outside, and the key word is matches. There is no pressure difference across your skin, no difference across any membrane, any cell wall, any tissue boundary. And without a difference, without what physicists call a gradient, there is no net force trying to compress or expand any particular structure. This is the real answer. It is not that the forces cancel because they push equally from all sides. It is that the forces cancel because your insides push out just as hard as the outside pushes in. You are a pressurized system in equilibrium with your environment, beautifully, silently, constantly in balance. The submarine, on the other hand, is a hollow steel shell with air on the inside at 1 atmosphere and an ocean on the outside at potentially hundreds of atmospheres. There is a huge pressure difference across that hull, and that difference is what provides the crushing force. The hull has to be strong enough to resist that difference by itself, go deep enough, and no steel on Earth can manage it. But here is the thought experiment that makes the principle crystal clear. And if you filled the submarine completely with water, so that the inside pressure matched the outside pressure at every depth, it would never be crushed, not at any depth. You could send it to the bottom of the Mariana Trench 7 miles down, over 1,000 atmospheres, and the hull would be perfectly fine. It would not deform by a single millimeter. Of course, it would not be terribly useful as a submarine, because the crew would have some rather serious complaints about the working conditions. But structurally, the hull would be in no danger whatsoever. The ocean cannot crush something that is already at the same pressure as the ocean. There is nothing to push against because there is nothing pushing back less from the other side. And now you see the real principle. Pressure by itself does not hurt anything. What causes damage, what causes motion, what causes all the interesting physics is a pressure difference, a gradient. Let me give you the simplest and most everyday example of this. You are sitting on an airplane. The plane starts to descend, and your ears begin to hurt. Everybody has felt this. It is uncomfortable. Sometimes it is genuinely painful. Children cry because of it. What is happening? Behind your eardrum, there is a small pocket of air. This is the middle ear cavity. It is connected to your throat by a narrow passage called the Eustachian tube. When the plane descends, the cabin pressure increases slightly as the plane drops to lower altitude. The air outside your eardrum gets denser and presses harder, but the air trapped behind your eardrum is still at the old lower pressure, because the Eustachian tube is normally closed and does not let air flow freely. So there is a pressure difference across the eardrum. One side is at the new higher pressure, the other side is at the old lower pressure. The eardrum, which is a thin membrane only about 1/10 of a millimeter thick, gets pushed inward by that difference. It stretches, it distorts, it hurts. What fixes it? You swallow or yawn or do that little jaw-wiggling thing that experienced flyers learn to do automatically. This temporarily opens the Eustachian tube and lets higher pressure air rush in from your throat to the middle ear cavity. The pressures equalize across the eardrum. The gradient disappears, and the pain stops instantly, as if you had flipped a switch. Notice what did not help your ear: the fact that the cabin pressure was equal in all directions around your head. The air was pushing equally on your face, on your chest, on the back of your neck. Symmetric, balanced, net force 0. And your ear hurt anyway because one specific membrane had different pressures on its two faces. That is a gradient. That is what matters. Now I want to push this idea further because it gets more interesting and more dramatic the deeper you go, and I mean that quite literally. A scuba diver descends into the ocean. Water is about 800 times denser than air, so pressure increases much faster underwater than it does moving through the atmosphere. For roughly every 33 feet of seawater depth, the pressure goes up by 1 full atmosphere. At 33 feet down, the diver experiences 2 atmospheres of total pressure. At 66 feet, 3 atmospheres. At 330 feet, 11 atmospheres. At the bottom of the Mariana Trench, nearly 7 miles down, the pressure exceeds 1,000 atmospheres. That is over 16,000 pounds per square inch. You might think a diver at depth would be crushed. But a diver at 33 feet breathing compressed air from a scuba tank is doing quite well. The regulator on the tank automatically delivers air at ambient pressure, meaning the air pressure in the diver's lungs matches the water pressure at that depth. 2 atmospheres outside, 2 atmospheres inside the lungs. The blood absorbs gases at 2 atmospheres. The fluids throughout the body are already at 2 atmospheres. Because they are incompressible and instantly transmitted the pressure from the surrounding water, everything equalizes. There is no significant gradient across any tissue, any membrane, any cell wall, and without a gradient there is nothing to cause damage. The problems begin when the gradients appear, and they appear in 2 ways that are both terrifying and deeply instructive. The first is something called a squeeze. If a diver descends and cannot equalize the pressure in some air-filled space in their body, a gradient develops across the boundary of that space. The most common example is the middle ear, just like on the airplane, except the pressure changes are larger and faster. If the Eustachian tube is blocked by congestion from a cold, the diver cannot equalize. The water pressure on the outside of the eardrum climbs, but the air on the inside stays at the old lower pressure. The eardrum gets pushed inward violently. Blood vessels in the middle ear can rupture. The eardrum itself can tear, from a pressure difference of sometimes less than 1 atmosphere. The face mask is another example. A diving mask traps a pocket of air over the diver's eyes and nose. As the diver descends, the water pressure outside the mask increases, but the air inside the mask is initially still at surface pressure. If the diver does not exhale through their nose into the mask to add more air and equalize the pressure, the low-pressure airspace inside the mask effectively creates a gradient that pulls on the soft tissues of the face. Blood and fluid are drawn into the eye sockets and the skin around the eyes. Divers call it mask squeeze, and photographs of severe cases are alarming. Bloodshot eyes, bruising across the entire face, sometimes swelling so bad the diver cannot see for days, all from a pressure gradient of a fraction of an atmosphere across a thin rubber seal. The second problem is even nastier, and it illustrates a different kind of gradient. This one is a gradient in time. It is called decompression sickness, or the bends. At depth, a diver is breathing air at high pressure, and the nitrogen in that air dissolves into their blood and tissues. Nitrogen is an inert gas. The body does not use it for anything. But at high pressure, according to Henry's law, more of it dissolves into the blood and fatty tissues, just as more carbon dioxide dissolves into soda water when the bottle is sealed and pressurized. The deeper the diver goes and the longer they stay, the more nitrogen their body absorbs. This is perfectly fine as long as they stay at depth. The pressure keeps the nitrogen dissolved and everything is in equilibrium. But if the diver ascends too fast, the surrounding pressure drops rapidly. And just like opening a soda bottle, the dissolved nitrogen comes out of solution. It forms bubbles. Tiny gas bubbles, right there in the blood and tissues. These bubbles can block blood vessels, starving tissues of oxygen. They can lodge in joints, causing agonizing pain. That is why it is called the bends. The pain in the joints made people bend over and writhe. If a large bubble or a shower of small bubbles reaches the brain or the spinal cord, the diver can be paralyzed or killed. What caused this? Not pressure. The diver was at high pressure the entire time they were at depth and felt perfectly fine. What caused it was a rapid change in pressure. And the outside pressure dropped, but the nitrogen dissolved inside the tissues had not had time to come out of solution slowly and safely through normal breathing. The inside was still at the old high pressure while the outside had moved to a new low pressure. A mismatch, a gradient, not in space this time, but in time. And that temporal gradient was what allowed the bubbles to form and do their damage. The fix for this is beautiful in its simplicity. You ascend slowly, very slowly, and you make stops along the way, hanging at certain depths for prescribed amounts of time. These are called decompression stops. At each stop, the diver waits while the excess nitrogen gradually diffuses out of the tissues into the blood, through the lungs, and is exhaled into the water, a little at a time. The pressure difference between inside and outside is kept small at every stage. The gradient is managed, controlled, held below the threshold, where bubbles would form. Patience defeats physics. Once you see this principle, you start noticing it everywhere. Let me show you something beautiful. Let us talk about how you breathe, because breathing is a perfect, elegant, everyday machine driven entirely by pressure gradients. You have two lungs inside your rib cage, connected to the outside air through your windpipe, your throat, your nose, and your mouth. Right now, the air inside your lungs is at atmospheric pressure. The air outside is at atmospheric pressure equal, so no air moves. You are in equilibrium. To inhale, your diaphragm, a dome-shaped muscle at the bottom of your rib cage, contracts and pulls flat. At the same time, your intercostal muscles pull your ribs slightly outward and upward. Together, these two actions increase the volume of your chest cavity. And here is where Boyle's law enters, one of the oldest and most reliable relationships in all of physics. Robert Boyle showed in the 1660s that for a gas at constant temperature, the product of pressure and volume stays the same. If you increase the volume, the pressure drops. If you decrease the volume, the pressure rises. When your chest expands, the air in your lungs has more room. Its pressure drops. Not by much, maybe 1 or 2% below atmospheric. A tiny difference. But that tiny gradient between the slightly lower pressure inside your lungs and the slightly higher pressure of the atmosphere outside is enough to push air down through your nose, through your throat, and into your lungs. Air flows in, not because you suck it in, but because the atmosphere pushes it in. The outside air is at higher pressure than the inside air, and air naturally flows from high pressure toward low pressure. When you exhale, everything reverses. The diaphragm relaxes back up into a dome, the ribs settle inward, the volume of the chest decreases, the air pressure inside the lungs rises above atmospheric, and air flows out. A gradient in the other direction drives the flow in the other direction. 15 times a minute, your body creates and then reverses a tiny pressure gradient. And that oscillating gradient moves about half a liter of air in and out with each cycle. Roughly 10,000 liters a day, all driven by a pressure difference of a few percent, invisible, silent, and absolutely essential every second of your life. Here is another example that makes people uncomfortable when they truly understand it. You drink through a straw. How the standard description is that you suck the liquid up the straw, but that word suck hides the real mechanism. When you put your lips on a straw and draw the air out of it, you reduce the air pressure at the top of the straw. The liquid in your glass still has the full atmosphere pressing down on its surface, 14.7 pounds per square inch. But the top of the straw now has less air pressing down. There is a pressure difference between the bottom of the straw, where the liquid surface in the glass is being pushed by the atmosphere, and the top of the straw, where you have removed some of the air. That difference pushes the liquid up the straw from the high-pressure region to the low-pressure region. You are not pulling the liquid. There is no pulling force in the straw. The atmosphere is pushing the liquid up, and you just created the conditions for that push to work by making one end of the straw have less pressure than the other. If you tried this on the surface of the moon, where there is no atmosphere, it would not work. You could suck on that straw until your face turned blue. Nothing would come up because there is no air pressure on the surface of the liquid to push it anywhere. And here is the limit. Even on Earth, with the full atmosphere pressing down, a suction pump can only lift water to a height of about 34 feet. That is the height at which the weight of the column of water exactly equals the atmospheric pressure pushing down on the reservoir below. Beyond that, no amount of suction can raise it higher, because you have used up the entire atmosphere's worth of pushing force. There is no more gradient to exploit. This limit actually puzzled people for centuries. The ancient Romans built aqueducts to carry water downhill over long distances, but they could never pump water uphill more than about 34 feet using suction pumps. They did not know why, they just knew it did not work. The Duke of Tuscany in the early 1600s wanted to build a decorative fountain that would send water higher than that, and he asked Galileo to investigate why the pumps failed at that height. Galileo, brilliant as he was, got it wrong. He suggested that a column of water broke under its own weight at that height, as if water had a kind of tensile limit, like a rope that snaps when it gets too long. It was Galileo's student, Evangelista Torricelli, who cracked it in 1643. Torricelli realized that the problem was not the water. The problem was the air. We live under an ocean of air that has weight, and that weight presses down on the surface of any exposed liquid. A suction pump works by removing air from above the water column, which creates a gradient. The atmosphere pushes on the reservoir, and there is less pressure at the top of the pipe. Water rises, but the atmosphere is not infinitely heavy. It can only push water up to the height where the weight of the water column equals the weight of the air column above it. After that, equilibrium. No more gradient, no more rise. Torricelli tested this by switching from water to mercury, which is about 13.5 times denser than water. He filled a glass tube with mercury, turned it upside down in a basin of mercury, and watched. The mercury column dropped to about 30 inches, 29.9 to be precise, and stopped. The space above the mercury was empty, a vacuum, the first deliberate vacuum ever created in a laboratory. That column of mercury was being held up not by any suction from above, but by the atmosphere pressing down on the mercury in the basin below. The gradient between the atmospheric pressure on the exposed mercury surface and the near-zero pressure at the top of the sealed tube was exactly enough to support 30 inches of mercury. We still measure atmospheric pressure in those units to this day. Barometric pressure, 30 inches of mercury, 29.92 if you want to be precise. Torricelli understood something profound. We swim at the bottom of an ocean of heavy air, and we do not notice it for the same reason that a fish does not notice the weight of the water above it. Everything is equalized. There is no gradient to feel. Suction is not a force. Suction is the absence of a force on one side. The gradient does all the work. And the gradient has a ceiling, because the atmosphere itself has a finite weight. This whole business about pressure gradients has a dramatic pedigree going back to the 17th century. Let me tell you about one of the most spectacular demonstrations in the history of science. In 1654, a man named Otto von Guericke, who happened to be the mayor of a German city called Magdeburg, did something extraordinary in front of the Holy Roman Emperor himself, Ferdinand III. He took 2 copper hemispheres, each about 20 inches across, fitted them together to form a hollow sphere, sealed the rim with grease, and then used a pump he had invented to remove the air from inside. With the air removed, there was a near vacuum inside the sphere, roughly zero pressure, and the full atmosphere 14.7 pounds per square inch pressing on every inch of the outside, a massive pressure gradient across the copper walls. He then hitched horses to rings on the outside of the hemispheres. 2 teams. The original demonstration at Regensburg used 30 horses, 15 on each side. When he repeated it in Magdeburg 2 years later, he used 16, 8 on each side. They pulled. These animals strained with everything they had, pulling in opposite directions. Ropes taut, hooves digging into the ground, and they could not separate the hemispheres. Not because the copper was welded or bolted. There was no latch, no mechanism holding the halves together. Just the atmosphere pressing inward on the outside surface with nothing on the inside pressing back. The gradient did all the work. The calculated force for a perfect vacuum inside those hemispheres would have been about 20,000 newtons, roughly equivalent to the weight of 2 small automobiles, all generated by nothing more exotic than ordinary air pressing on copper. And then von Guericke opened the valve. Air rushed back in. The pressure equalized instantly. Inside matched outside. The gradient vanished. And the hemispheres, which a moment before had resisted the strength of 30 horses, fell apart in his hands like 2 halves of an apple, as if they had never been joined at all. That is the power of a pressure gradient, and that is the harmlessness of pressure alone. The atmosphere was always there, pushing on those hemispheres with the same 15 pounds per square inch. It pushes on everything else. But as long as the inside matched the outside, the hemispheres could be separated by a child. It was only when the inside was emptied, only when the gradient appeared, that the force became irresistible. I want to go somewhere deeper with this now, because what we have been discussing is not merely a trick of atmospheric pressure or an entertaining demonstration. It is a fundamental principle in the physics of fluids. In fluid mechanics, there is a concept called the pressure gradient force. The mathematics tells you something that confirms precisely what we have been saying through examples. In a fluid at uniform pressure, with the same pressure at every point in space, there is no net force on any small parcel of that fluid. 0. The pressure pushes equally on all 6 faces of every tiny cube-shaped volume element, and the pushes cancel perfectly. It is only when the pressure varies from point to point, when there is a gradient, that a net force appears, and that net force always points from the region of higher pressure toward the region of lower pressure. This is why wind blows. The sun heats the Earth's atmosphere unevenly. Land heats faster than ocean. The equator heats more than the poles. Dark soil absorbs more than white sand. These uneven temperature patterns create uneven pressure patterns. Where the air is warmer, it expands, becomes less dense, and the surface pressure drops slightly. Where the air is cooler, it sinks, compresses, and the surface pressure is slightly higher. A gradient forms between the high pressure zone and the low pressure zone. Air flows along that gradient, from high to low. That flow is wind. All wind, from the gentlest summer evening breeze to the 200-mile-per-hour fury inside a tornado, is driven by pressure gradients. The wind does not care about the absolute pressure at any point. A gentle breeze can blow at sea level, where the pressure is 1 atmosphere, or on a mountaintop where the pressure is 2/3 of an atmosphere. What matters is not the pressure at any single location, but how rapidly the pressure changes from that location to its neighbor. The steeper the gradient, the stronger the wind. A tornado is an extreme case. At the center of a powerful tornado, the air pressure can drop by as much as 10% below the surrounding atmospheric pressure. That sounds modest, 10%. But 10% of 1 atmosphere is about 1.5 pounds per square inch. And spread over the walls and roof of a house, that small percentage translates into forces of thousands of pounds, all pulling outward. The house, which was perfectly happy with equal pressure inside and outside, suddenly has more pressure inside than outside. The walls and roof are being pushed outward from within, and if the structure cannot vent fast enough to equalize, it can blow apart, not from the outside in, but from the inside out. People sometimes say that a tornado ripped a building apart. In many cases, the building's own internal air pressure did most of the work. The tornado just removed the matching pressure on the outside. And while we are talking about pressure variations in air, let me point out something you might not have considered. Sound itself is a pressure gradient. When someone speaks to you, what reaches your ear is a traveling wave of alternating high and low air pressure, tiny compressions and rarefactions, rippling through the air at about 770 miles per hour. At each